Well, good evening, everyone. Nice to see so many people come out on a Monday night and snow and everything else. It's really appreciate you being here. Obviously, this subject stirs interest, and great to see so many people from the community. Sometimes when we have talks here, we get good community representation, and sometimes it's just a bunch of us students and faculty. So, I'm Chris Stanley. I'm a member of the Theology faculty here, and I'm just pleased to be able to have Tony Ingraffea here with us tonight. This talk tonight is co-sponsored by the St. Bonaventure University Visiting Scholars Series, the St. Bonaventure University College Democrats Group, and the Tread Lightly Campus Environmental Group. Just real quickly, I thought I'd acknowledge the heads of the two groups here in case for students, if you wanted to talk with any of them afterwards and get signed into anything, there's an opportunity there. So just a few words about Tony. Tony Ingraffea is the Dwight C. Baum Professor of Engineering and the Weiss Presidential Teaching Fellow at Cornell University. He also serves as President of Physicians, Scientists, and Engineers for Healthy Energy. His research centers on computer simulation and physical testing of complex fracturing processes. He and his students perform pioneering research in the use of interactive computer graphics in computational mechanics, producing over 200 papers in these areas. He's been a principal investigator on over $35 million in research and development projects from a variety of government agencies and private corporations. In 2005, Dr. Ingraffea was named co-editor-in-chief of the journal Engineering Fracture Mechanics. Notice how all these actually have the word fracture in the title. He knows what he's talking about in the science here. In 2006, he received the ASTM Irwin Award for meritorious contributions to the practice of fracture mechanics. And in 2009, he was named a Fellow of the International Congress on Fracture. In 2011, Time magazine named him one of its People Who Matter. Now that sounds pretty impressive to me. In recent years, Dr. Ingraffea has given numerous speeches to the general public in New York and other states about his experience of moving from an industry insider to a science-based critic of the practice of hydraulic fracturing. So without further ado, I will introduce to you Tony Ingraffea.
Good evening, everyone, and thank you very much for coming tonight. Wasn't there something better to do on a Monday night in Allegheny? Not for me. I'd much rather be here than home in Ithaca tonight. Seriously, thank you all for coming out. I consider it a responsibility of mine to make it your worthwhile. I'll do my very best to inform, educate, answer questions. So some ground rules before we get started. We'll try to save the questions till the end, somewhere around 10:30. Checking your sense of humor at this point. I'm glad it stays intact. We're going to have a good time tonight. But one ground rule is that if you detect that any time while I'm talking to you, I'm saying something that you think is inaccurate, or worse, untrue, please stop me then. Don't wait till the end, and I'll try to address any inaccuracies or things that you perceive to be as untrue as quickly as possible. It's important that I not get through all 424 slides tonight. What's more important is that you get as much out of what I'm going to talk about as possible, and that means a give and take when necessary. So Chris and I went over a number of times what the title of this talk, and we finally agreed that this was the title that would attract all you here. It had to have the word fracking in it. I was vehemently against having the word fracking in the title because it's such a controversial word, and it's so prone to misunderstanding and ambiguity. So I'll try to avoid using it tonight, but I'll explain everything as best I can about what fracking is, but more importantly, what comes before fracking and what comes after fracking, because I think those are far more important topics for you and the potential impact that the shale gas, the development of methane from shale formations in New York might mean to your health, your welfare, your environment, your climate, and your property values. So let's proceed. And has anybody ever heard me talk before? Seen anything? Uh-oh. I guess I got to do it right tonight. Those of you who haven't heard me talk, it's always difficult to get started, as you notice. I'm just treading water here, trying to figure out, watching the faces and getting the reactions, how to address so many topics in the science, the technology, and the engineering of how to get methane, what you would call natural gas, how to get methane out of a shale formation. And so recently I've been using a theme, a motif, an approach which is based on myths and realities. As you know, a myth is a story. We tell our children stories. A myth always starts with a kernel of something which is believable, something that you really think, hope is true. But a myth is an embellishment. It's something beyond truth. It's an attempt to get someone to understand or see something that isn't really there. On the other hand, what we call reality is what engineers call ground truth. It's as close to truth as a philosopher would allow us to declare something to be. So myths. There are 4 statements on that board right now, each of which, as they're written, is true. I'll let you read them. And hopefully, before the night is over, we will explore each of those 4 statements in some depth. We'll find out what the truth is at the kernel, at the heart of each of those statements. And then hopefully I'll inform you as to why these statements have become larger than truth. They become mythological. Hopefully we'll have time to get through all 4. You've heard them all on TV advertisements. You read about them in magazine articles, letters to the editor, op-eds. You've been told that fracking, and I'm spelling it correctly there, fracking is a 60-year-old well-proven technology, the implication being, what harm could it do if it's already been done for 60 years and it's well-proven? We'll investigate that. The next is, well, to get shale economically, to get gas economically out of a shale formation, you have to use what are called multi-well pads. And I'll explain what all this jargon means as time goes on. And those pads have to be constructed in a clustered arrangement. And if you cluster multi-well pads, you're going to reduce surface impact. So we'll explore what that means. The implication there is you shouldn't worry about shale gas development in this region because it's not going to cause any more surface impact than what you have seen by oil and gas development in this section of New York. In fact, you'll see less. That's what we're asked to believe. Next, leaky wells hardly ever happen. Fluid migration from faulty wells is a rare phenomenon. Well, rare is one of those words that you might use in a restaurant to differentiate between well done and medium well. Rare to some people might mean once in a blue moon. So let's decide by the time the night is over whether you think what the industry claims is rare enough for you. And finally, natural gas is a clean fossil fuel. And the word clean here doesn't have the implication of soap and water. The word clean here has the implication of better for climate change, not as bad for climate change. So those are the 4 topics we're going to investigate tonight, and I'm looking forward to interacting with you on them. And so let's dive in. Fracking is a 60-year-old well-proven technology. Why should we worry about it? It's been done in New York State since the late 1940s. There's over 1 million fracked wells in the United States alone. It's a well-proven technology. We shouldn't worry about it. Not true, in my opinion. Why? Because we're not just talking about the kind of fracking that's been done in New York State since the late 1940s. We're talking about the kind of fracking that has never been done in New York State. Why is it different? Why is development of methane from a shale formation called unconventional? Lots of reasons. From the industry perspective, let me give you 4 reasons. In order to get methane out of a shale formation, you have to combine 4 technologies that only recently came together. That's different than saying they're all new. Some of these technologies are old, some of these 4. But combining them in a particular way, I'll show you, is only about 5 or 6 years old. And on the way to explaining each of these 4 technologies, we're going to do what I refer to as Shale Gas Development 101. I'm going to tell you a lot about the science, technology, and engineering of how an operator gets methane out of a shale formation. So for those of you who are new to this and really want to understand what actually has to happen, here you go. This is everything you need to know quickly in about 5 minutes. The 4 technologies, one is directional drilling. it means exactly what it says. So to use a schematic, typically wells are drilled vertically, more or less vertically, and typically they're drilled not into shale to produce gas or oil, but into carbonate rocks or other rocks that are not sources of organic material. They're trap rocks. This is not a picture of a trap rock situation. This is a picture of a shale gas situation. So in addition to drilling vertically, directional drilling means that they can turn the drill bit and follow the shale. In fact, in modern shale gas development, the vertical part of the well isn't as long as the so-called lateral part of the well. The reason for that is quite simple. Whereas in a traditional oil or gas well, like the 40,000 of them in New York State, where the gas or oil is trapped directly below the well pad, hopefully, otherwise you get a dry hole. With shale, the gas is distributed throughout the shale layer. Not uniformly. There's some parts of the shale that have more gas, some parts that have less. But you want to get the gas out of as much shale as possible, and if you only drill into the shale, which might only be 100 feet thick, directly below our feet, why drill a 5,000-foot hole to only encounter 100 feet of shale? Doesn't make economic sense, and it isn't economic sense, and that would not be done except for exploratory purposes. Find out if the shale was down there and if it has any gas. Rather, you want to drill the well so-called laterally, not really horizontally because the shale isn't necessarily horizontal, but laterally so that much more of the well comes in contact with the shale. So technology number one that had to come around had to be available. Otherwise, shale gas development is not possible, is directional drilling. Directional drilling has been around since the 1970s for commercial purposes. So it's not a new technology. It's been used many times, but only recently for shale. But along with every one of these opportunities, like directionally drilling in shale, comes other problems. That's what engineers do. They solve one problem and create another one. That's what keeps us busy. So I'm going to show you another picture and tell you why the next technology, high frac fluid volumes, is necessary. So we're going to go to a shale formation. This one is on the surface. It's in Tagonic Falls Gorge. Many of you have walked up Tagonic Falls Gorge, I hope. So this is an exposed layer of shale. It's not the Marcellus, it's not the Utica. Okay, it's the Geneseo Burkett. It's a black shale. It once had a lot of gas in it. So let's see, we're going to test the IQ of people in Allegheny. I'm sure you're all above average. Look at these lines. And those of you who heard me talk before, you can't answer. What are these lines? I've taken visitors from out of state up that gorge, and when they look at those lines, their first question is, who sawed those lines in the rock? What are those lines?
Fracture lines.
Yeah, they're fractures. They're called joints in geological terms. How'd they get there? Mm-mm. Good guess. Wrong.
Freezing, thawing.
Nope. Good guess, but wrong.
Gas.
Movement.
Gas. Those are natural hydraulic fractures. Those are formed by gas pressure. There was gas in that shale formation. When that shale formation was 1,000 feet underground, a couple 100,000 years ago, the gas pressure was sufficiently high in that shale that it fractured the rock. Ooh. Those are natural hydraulic fractures. Hydraulic doesn't necessarily mean with water. Hydraulic just means with a fluid. A fluid can be a liquid or a gas. So in this case, gas pressure fractured the rock. So these are natural hydraulic fractures, in this case 2 sets of them. And in order to produce economically methane from a shale formation, it must already be fractured. Whoa. What do you mean by that? Okay, shale itself. Take that block of shale right there, roughly a yard by a yard. Shale itself is impermeable. It has about the same permeability as steel. How easy it would be, how easy do you think it is to get a molecule of methane to go through 3 feet of steel? Possible. Takes a while. It takes about as long to get through 3 feet of shale. But wait a minute, Professor Ingraffea, you just said there's a lot of gas. or there was a lot of gas in this shale. There's a lot of gas in Marcellus and Utica, but it's locked up in the shale, so how do we get it out? You get it out where it's already come out. Where has it already come out? What caused those fractures? Methane. Where is the methane after it caused the fractures? Did it disappear? Did it burn? It's still there. Oh, so wait a minute. To get shale gas out of a shale formation, it has to already be hydraulically fractured naturally, and we have to get access not to the shale itself, but to the fractures in the shale. How many people knew that before they came here tonight? Good. All right, so how are we going to do that? Here's the lateral. Here it is again. And remember, that can be 5,000, 7,000, 8,000, 10,000 feet long. It's the lateral. It's a steel pipe called production casing. And we want to get the gas that's currently stored in all these natural fractures to go into that steel pipe. What's the next thing we have to do? Once we drilled the hole and inserted that steel pipe all the way down to the end of it, and that's about 3 miles of steel pipe, what's the next thing we have to do? No, that's not the next thing, but we're going to do that. What's the next thing we have to do? That's a steel pipe. We've got to perforate it, punch holes in it. All right, that's the perforation process. Punch a lot of holes in it. Where do you want to punch the holes?
Where the zones are.
Well, hopefully you align the holes with where the cracks are, but do you know where the cracks are? Not really. You know they're down there because you've done explorations, geological explorations, and you know more or less the spacing, but you don't know exactly where each one of those cracks are. So you punch thousands and thousands of holes along that 5,000 to 10,000 feet of steel pipe. Now what do you got to do? You got to get the gas, which is stored in those cracks, which are being squeezed shut by the earth pressure. Now be careful when I say squeeze shut. Right? They're not squeezed shut completely. They're partially open, partially cemented. But compared to the width of a methane molecule, how wide is a methane molecule? 1 times 10 to the minus 9th meters. How wide does a crack have to be to store a hell of a lot of methane molecules? Not very. But on the other hand, you'd like to open that crack a little wider, up to maybe a millimeter, so that the gas can more freely flow out of those cracks back into the holes in that casing and up the casing and out the well. That's why we have to use human hydraulic pressure to re-fracture the shale. Now, what do you mean? Well, they're already there. What we want to do is open them a little bit more so they become what we call superhighways. All those gold lines are meant to be a flow pattern. Think of it as a traffic pattern. You're a methane molecule over here. You're going to go down this street, take a right, go down that street, go down through that perforation and up the casing. So we inject fluid, hydraulic fracturing fluid, into the casing, out the perforations, into the already existing fractures, reopen them wider so the gas can flow more freely, and the gas that's immediately adjacent to those natural fractures can come out of the shale slowly over a matter of years and add to the flow. But we can't keep the pressure down there forever. You can't pump 5 to 10 million gallons of frac fluid down there and keep it under pressure forever, because now that frac fluid is in the way. The gas can't come up. We got to get the water, the frac fluid, to come out of the well. But when we do that, the fractures would close up again. So part of what we send down the well in the fracking fluid is proppant, little beads of sand or little ceramic beads that follow the flow down the casing, out the perforations, into those natural fractures, so that when we relieve the pressure from the pumps on the surface, those cracks can't slam shut. They can't go any closer back together than the diameter of the sand particle or the ceramic bead. So now we have a super highway. That's the whole idea behind hydraulic fracturing. You reopen existing fractures, which are storage reservoirs for natural gas, and become the immediate source for production from a well. All right, so what do I mean by high frac fluid volumes? Well, in the state of New York, up until recently, it was illegal to frac a gas or oil well with more than 80,000 gallons of frac fluid. The recently proposed, but now defunct, new regulations would have allowed 300,000 gallons per frac job. The average in Pennsylvania right now is 5.5 million gallons per frac job, per well. The record in the United States, as far as I know, is 42 million gallons in one well. So it's about a 2 order of magnitude increase from 80,000 gallons to 5 to 10 million or more. And the reason why you need all that frac fluid is because you're trying to open as many of these fractures as possible as far as you can in this direction and in this direction, and all the way to the top of the shale and all the way to the bottom of the shale. That's acres and acres of fractures you're opening. Takes a lot of fluid. Right? How are you going to get 5 million gallons of frac fluid down a 4.5-inch diameter steel pipe, 3 miles at 10,000 pounds per square inch in an hour? How many hydraulic engineers do we have in the audience? How many volunteer firemen do we have in the audience? Okay, let me say that again. You want to get 5 million gallons of frac fluid through a 4.5-inch diameter pipe, 3 miles long, at 10,000 pounds per square inch in about an hour. How much horsepower do you need at the surface to do that? It's impossible to do that unless you invent slick water. It's impossible because the frictional dissipation of the frac fluid along the pipe would be so high that no matter how much pressure you apply at the surface, you'd never get flow at the end. That's like having an infinitely long garden hose. Did you ever try that? Hook a garden hose to the faucet in your house. The first 25 feet, you get good flow. The next 50 feet, not much. Put a 100-foot extension, all you get is dribble out at the end. So somebody had to make the frac fluid more slippery. So chemists got together and figured out how to make slick water, how to add a lubricant to the frac fluid so that it would flow more easily. More easily meaning now you need 10 to 15,000 horsepower during a frac job. I'll show you a picture later of a typical frac job about 20 miles south of here, 16,000 horsepower of pumps. So those are 3 technologies. This is recent, this is recent, this is not recent. But it turns out that you still can't economically develop methane from shale without this technology, multi-well pads and cluster drilling. So now I'm going to explain to you what that is. Another picture. You'll notice that whenever I'm giving you information or data, I'm telling you what the source is, so you can go check it on your own. This is a photograph out of National Geographic from last December. These are 2 ExxonMobil engineers in a 3D cave, a virtual environment for visualization. They're wearing those glasses that you're wearing to go to 3D movies, and they're actually inside of the Marcellus Shale Formation. Here's the surface. Here are the vertical parts of the wells. Here are the lateral parts of the wells. Here are all the different layers of rock. Here's the Marcellus shown in red. Let me show you that another way. This is a picture taken by Shell. Here's the surface of Tioga County, Pennsylvania, topographic map of a portion of Tioga County, Pennsylvania. Here's the Marcellus Shale, a region of Marcellus Shale under that part of Tioga County. Notice it's not flat, it's not horizontal, it is what it is. It's bent, folded, it is what it is. Here's fault, right down to there, there's another one over here. Each one of what appears to be a single well here is a collection of wells. So here's a pad, that's the area at the surface where the drilling occurs. And here were 6 wells coming down from that pad, splaying out, 3 of them going north-northwest, 3 of them going south-southeast. You come about 3/4 of a mile over here, here's another pad. It's got 5 wells on it so far. Another 3/4 of a mile, here's a pad that only has 1 well so far. Another pad, another well. All right, so I'm still testing your IQ. If there's gas everywhere here, where do you want to drill? Thank you. Told you were above average. So they haven't finished drilling everywhere here, but you're getting the idea. On the surface, there will be a clustered arrangement of pads. Hopefully, the landowners will lease you the land for the pads, so you have clustered arrangement of pads, and on each pad you have many wells. That's been found to be the only viably economic way, when the price of gas is high enough, to produce gas economically. Right now, the price of gas isn't high enough to make even this worthwhile for dry gas. So this one's from Chesapeake. This is something on their website that shows a clustered arrangement, pad, 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 just like a checkerboard on the surface. And from each pad, in this case, there were 6 wells. Here are the laterals. These are supposed to be the fracture patterns. Artist's conception, it's not really what it looks like. But that's multi-well clustered pad arrangement. So those 4 technologies, directional drilling, high frac fluid volume, slick water, and multi-well clustered pad arrangements are necessary in order to hope to get methane, dry gas, out of a shale formation economically. Let me show you how it works in practice. This has all been hypothetical. Dallas-Fort Worth Airport. Those of you who don't know should know that shale gas development in the U.S. started in Texas, modern shale gas development, in the Barnett Shale play, just to the northwest of Dallas-Fort Worth. Just to the northwest of downtown Dallas-Fort Worth is the Dallas-Fort Worth Airport, owned by the cities of Dallas and Fort Worth, and they leased the entire airport property to Chesapeake. And Chesapeake used that entire property to develop shale gas. So that's what it looks like from Google Earth. That's what it looks like for the shareholders of Chesapeake. That's the same map of the Dallas-Fort Worth Airport, but every one of these red dots is a pad. And every one of those red lines is a lateral. So on the Dallas-Fort Worth Airport, they constructed 53 pads and drilled about 200 wells. That's called spatially intense development. Clustered multi-well pad arrangements with long laterals. This is where it was all experimented with and developed. These laterals aren't that long. They're only 2,000, 3,000 feet long. These were all done in the early 2000s. So, summarize. Remember, the myth is, or the kernel of the truth of the myth is, fracking has been around for 60 years. That's true. But what I just showed you is a kind of fracking that has never happened in New York State. And it only began to happen in combination of those 4 technologies in 2007. So the technology involving fracking is an implementing sub-technology. That's what industry calls it. An implementing sub-technology. It's necessary, but it's not sufficient. It's a sub-technology because you can't frack unless you drill. Drilling is a technology, fracking is a sub-technology. So here's where things happen. First horizontal well drilled, 1991. Slick water fracturing is invented. Fracturing fluid invented in 1996. Multi-stage fracturing. You don't fracture the entire well at one time. You do it in stages. In 2002, and the use of multi-well pads and cluster drilling perfected for commercial uses in about 6 years ago. So what? The myth, fracking for gas development is a 60-year-old well-proven technology. You shouldn't worry about it. We've been doing it forever. You've never done it in New York State. And doing it involves 4 technologies, which had to be combined for the first time only 6 years ago. So at this point, there aren't 1 million shale gas wells fracked in the world. There are fewer than 30,000. And those 30,000 have been fracked by over 300 companies. So how much corporate experience is there in shale gas development? There's no one company that can claim that they fracked 10,000 wells or 1 million wells. So what? Unconventional development of methane using high-volume fracking from multi-well clustered pads with long laterals is not a 60-year-old well-proven technology. I just showed you that it's about a 5-year-old, still unproven technology. It's still under development. If it wasn't still under development, the industry would be spending tens of millions of dollars, each major company, doing in-house research and sponsoring research in universities and national labs to figure out how to make it work better. Fewest dollars down the hole for the most gas out. You can read any of the literature, as I do. I read all the literature, read any of it on shale gas, industry literature, and it all says the same thing. We haven't quite figured this out yet. There's got to be a better way of doing this. So what? Well, there are health impacts. We have had insufficient time to conduct the necessary studies, health impact studies, climate change studies, economic studies, and sociological studies, because this is a spatially intense, invasive industrial activity. You're not going to have a pad 1 mile outside of Allegheny and see the next one in the next county. Insufficient time to conduct the scientific investigations of impacts due to the process itself and due to the inevitable accidents that accompany any industrial activity. Okay, that was myth number one. And I hopefully gave you a little bit more reality to it. Now that you know what a multi-well pad is, and you know what a clustered pad arrangement is, we can get to the second myth. So this myth is mythological for two reasons. One is it's irrationally illogical. What is less than 0? Well, if you're a mathematician, you say a negative number, right? Is there any surface impact from shale gas development in New York State right now? No. So how can there be less if we have it? Okay, you didn't get it. Okay, so what the industry is, remember, there's a kernel of truth here. The industry is saying, actually, if we use the technology we've always used in New York State, one pad, one well, one pad, one well, if we use that same technology, we'd have to have a pad about every 1/10 of a mile with one well on each pad. And that would cause a lot of surface disruption because you'd have a pad every 1/10 of a mile in every direction. And they're trying to get us to believe that by doing multi-well clustered pads, you won't have all that. But the problem is that they would never do the former. There's no economically viable way of putting one pad, one well on one pad, with one pad every 1/10 of a mile. They would never do that. It's economically impossible to develop shale gas using that technology. You're an owner. Are you going to drill one well on one pad, go through the trouble of leasing, building, constructing access roads, pipelines to that one pad, bring the drill rig in, drill one well, bring the fracturing rig in, fracture the well, then move everything 1/10 of a mile? So you're comparing apples and oranges. But let's talk about surface impact. And let's talk about it in real terms, not hypothetical terms. So we'll go to northeastern British Columbia, which is where currently all the active, what we call avant-garde, boutique research is being done. If you're going to try to push the envelope of shale gas development, you go someplace where there's no pushback. New York State is not a place where there's no pushback. Okay? So this is northeastern British Columbia. You notice the heavy population here of protesters and activists. So last year, this was declared the largest frack job in the world in shale. There's 16 wells on this pad. That does not look like any of the pads that you see around New York State with a single well on a single pad. This is the future of shale gas development. Large pads, 16, 20, 24 wells per pad. That's the way the industry is moving. So that is a typical surface impact for a 16-well pad. Go to Pennsylvania. Here is a 5-well pad. Again, this is not 2 acres, which is typically what you see in New York State for a single well on a single pad operation. In Pennsylvania, even today, they're allowed to use waste pits to store fresh water to begin with, then to store drilling fluid, and then eventually to store frac flowback fluid. We've yet to see whether that's going to happen in New York State. We don't know yet because we don't have regulations for shale gas fracking in New York State yet. Also in Pennsylvania, this is a 7-well pad, and these are all going to go, there'll be more wells on each of these pads. How many trees were killed? What I should be doing is telling you the regulations that we should have in New York State, one of which should be, for every tree you kill, you plant 2. After all, we're all green, right? All right, some of the other infrastructure associated with surface impact, it's not just the wells, it's not just the pads. There are other things called surface infrastructure which are necessary to produce shale gas economically. So here you see a 7-well pad. This was the impoundment pond, condensate tanks, storage for chemical tanks. Another example, a well pad, a well pad, a well pad, frac wastewater pit, compressor station, processing facility. So what are compressor stations and processing facilities? A compressor station is a facility that increases the pressure of the gas in the pipelines. The gas that's coming out of the well on the first day might be at a few hundred pounds per square inch of pressure. By the end of the first year, it's half of that. By the end of the second year, it's half of that. But to get the gas into a transmission pipeline, to send it to Boston or New York, it has to get increased to about 1,000 pounds per square inch. That's the operating pressure for transmission lines, about 1,000 pounds per square inch. So the idea here is the gas comes in at a low pressure, goes out at a high pressure. So there are high pressure pumps in here. Again, 3, 4, 5, 6, 1,000 horsepower centrifugal compressors running 24/7, 365. And if the building is not soundproofed, you hear it 24/7, 365. A processing station is a mini refinery. If the gas coming out of the ground is wet, it doesn't mean it's got water in it. When gas comes out of the ground, it always has some water in it. If it's wet, it has other hydrocarbons in it, natural gas liquids, ethane, propane, butane, for example. You got to separate those out. That's what a refinery does. It separates hydrocarbons. So wet gas will come in here, and what goes out into a pipeline would be natural gas, methane, and what goes out into tankers would be propane, butane, ethane. We don't know here whether the Utica is wet or dry. We're pretty sure that the Marcellus is pretty dry, so we don't know yet whether we're going to need processing units in New York. We'll find out. Surface impact. I know many of you are probably contributed to writing to DEC comments about its SGEIS and the proposed regulations. I suspect many of you wrote comments, and many of you probably wrote comments about setbacks. And you were probably, like most people in New York State, myself included, initially myopic, thinking, well, if we just get the wells far enough away from homes and schools and hospitals and water bodies, we'll be safe. But as I just showed you, wells aren't the only part of the surface infrastructure. Ask the people living in these homes. There's no wells here. But the company came in and put a waste pit. This was a super mister. So they took, this is a pit that's used to store frac fluid for later recycling and reuse. That's good. Recycling and reuse is good, except you got to store this stuff for a while. And so they built a 3-acre pond, and it's kind of hard to see because it's too bright in here, but each one of these is a fountain. You're spraying this stuff up in the air so that they evaporate off the VOCs, volatile organic compounds. So the people that built their Mac mansions here thinking they were going to have the life of Riley.
Can you go back to that slide? Can you talk about the containment a little bit?
Talk about the what?
The containment.
Okay, this is a human-made pond. It's been constructed. It's lined, probably by Pennsylvania law, double lined with a plastic liner to inhibit leakage, but there's no cover over it.
That impoundment leaked, and those people are currently in court suing the company because their water wells are contaminated.
Yeah, I
And
didn't
their
want
health
to
is impacted.
didn't want to mention any names here, but yeah, these people are in court. Okay, I told you I was going to show you a recent frac job. This is from January of this year. Here the location, here's the location, Evans City, Pennsylvania. Each one of these units is a 1,000 horsepower pump. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And there are 4 wells. So they're going to frac each one of those 4 wells in succession, 16,000 horsepower. So again, there's a lot of noise and VOC emissions going on while that's happening. And as you can see from the snow, it's happening 365. There are people who think that what happened at the Dallas-Fort Worth airport couldn't happen here because we're hilly and Dallas isn't. I've had people from industry say, Professor Ingraffea, you're exaggerating. We can't put wells and pads everywhere. That's a mountaintop. Here's a, you realize, anybody here in the construction industry, you know how much fill it took to build that? That's thousands and thousands of truckloads of fill brought in, and so they can build a pad off the side of a mountain. Here they had to excavate out the side of a hill in order to build that pad. So the point is that they can build pads just about anywhere. Now they might say, well, 15% slopes is the limit, but it's the limit right now when there are easier places to drill But as I said before, the gas is just about everywhere, and eventually they're going to try to get everywhere unless there are enforceable regulations. The last point I want to make on this particular myth is that you should know that the shale gas revolution in the US is just getting started. Commercially, it really didn't reach full speed until about 5 or 6 years ago in Texas, then Arkansas, and Louisiana, and then Pennsylvania. It didn't start in Pennsylvania until about 2007 commercially. So in Pennsylvania, as of now, there have been something like 6,800 Marcellus wells drilled. About half of those have been fracked and put into production. And industry estimates that they will drill 100,000 Marcellus wells in Pennsylvania. So from the fracking point of view, they're about 3% of the way in to what they're eventually going to do. From a well drilling point of view, they're about 6% of the way in to what they're eventually going to do. So there are vast areas of Pennsylvania you can drive through right now and not see a darn thing. But I'll show you some pictures of what it's going to look like in just a minute. All right, so still talking about surface impact. How will things happen in New York State, and is it different from what happened in Texas, Arkansas, Louisiana, Pennsylvania, West Virginia, Ohio? I'm going to use some jargon here so you get familiar with it. Those of you who have leased your land, I'm sure there are people here who have leased their land, should know something about a spacing unit. If you leased your land, you're part of a spacing unit, or will be part of a spacing unit. By legal definition in New York State, a spacing unit is an area defined by the operator and proposed to DEC as an area in which that operator wants to develop shale gas. So this is a spacing unit. This is a spacing unit. These were indicated on applications, in this case from Chesapeake, to DEC. So Chesapeake went and contacted all the landowners inside that spacing unit, and when they got permission from landowners that controlled 60% of the land in that spacing unit, they now had a green light. They could apply for a permit. So there's 3 parties involved here: the operator, DEC, your legal representative in New York State, and the landowners. Once the operator has the permission of the owners who control 60% of that land, compulsory integration kicks in. Compulsory integration says the other 40% now have nothing to say other than send me a royalty check. But that royalty check is going to be limited to 12.5%. The other people can negotiate for whatever they want. So that's a spacing unit. What defines a spacing unit area? Technology. So if I'm going to put a pad here, and I want to drill 4 wells north-northwest and 4 wells south-southeast, and I want each lateral to be 1 mile long, that's 1 mile, that's 1 mile. How long should the spacing unit be? A little over 2 miles. If I want to have 4 wells and I want to have 500 feet between each well, 1, 2, 3, 4, that's 2,000 feet, plus 500 more is 2,500 feet, which is a half a mile. 2 miles by half a mile is a square mile, 640 acres. Take a look at the proposed regulations that are no longer on the books. The industry asked for and got from DEC the permission to increase spacing units to 640 acres. What determines the orientation of the spacing unit? Remember, you're above average intelligence. You proved that to me. Your IQs are very high. Where do you want these laterals to go? What are they supposed to intersect?
Follow the shale.
The natural fractures. Will they know the direction of the natural fractures? They sure will. In this area of the country, the natural fractures are going to be intersected most if the wells are drilled north-northwest and south-southeast. So what would it look like? Well, here's Almond, a little bit east of here. Here's Pennsylvania state line down here. And there would be an ideal arrangement, low leftover space, no openings, no gaps. Every yellow rectangle would be a spacing unit. Every red dot would be a pad location. And they would drill 6, 8, 10 wells in each direction. That would be an ideal arrangement, similar to what you saw on the Dallas-Fort Worth Airport. So for this to happen, you'd either have to get one operator to get all that land. One operator would have to get the permission of the people who own all that land, who own 60% of that land, to say yes. That's not likely, because the operators are all competing with each other. And you'd have to get all the landowners to agree, but that would be ideal. Yeah, that would make all the boards of directors of all the gas companies in the world happy. They could do that. This is how it's actually happening in Pennsylvania. So here's Tioga County, Pennsylvania. This is a map produced by Shell for the EPA. It shows all of Shell's lease holdings in Tioga County, in case you wanted to know. Tioga County has been leased out by a number of different operators, not just Shell, but these are Shell's holdings. And you can see here, north-northwest, south-southeast. I'll blow it up. North-northwest, south-southeast. Each of these is a spacing unit, what we would call a spacing unit. It's called a development unit in Pennsylvania. Hold on one sec. Each black dot would be the future location of a pad, and that's how development would work. So here's Wellsboro. Here's Mansfield.
Very good.
Somebody had a question here. Was I say something inaccurate?
The colors, what do the colors represent? Is that
Um,
elevation or?
You know, I've been trying to figure that out myself. There's a code down here, but I don't know what it is. It's probably total organic content. I'm guessing. It's some measure, it's some indication of how good the wells are going to be. I'm guessing. Obviously, Shell wasn't willing to give me the original. I asked. Okay, so the myth is the use of multi-well pads and cluster drilling reduces surface impacts. The truth, in my opinion, is the use of multi-well pads and cluster drilling facilitates and prolongs surface impact. We don't have any surface impact around here right now. Certainly no surface impact in Tompkins County where I live. So if you're going to come in and start building clustered pads, a pad 3/4 of a mile in every direction, and each one of those pads is going to have 8, 16, 12, 20 wells, and it's going to take years for each of those pads to be built out and fracked, that's not a reduction in surface impact. That's just a heck of a lot of surface impact over a long period of time. So what? Why should I be concerned? Why should you be concerned? Because you're going to have long-term noise, dust, light pollution, oxides of nitrogen being produced because you're burning a lot of diesel while you're drilling and while you're fracking, higher spill probabilities because you have high frac fluid volumes, venting and accidental emissions of gases. Those are health impacts. Do we know yet what, by scientific investigation, the extent of those health impacts? No. Have we traded off the cost of remediating those health impacts to the alleged economic benefit of developing the shale gas? No. So New York State is smart. We're waiting for the science to be done. You don't do policy before the science says what policy you should do, in my opinion. Next, fluid migration from faulty wells is a rare phenomenon. Don't worry about your private water well. We're not going to contaminate it. No possibility whatsoever that your water well will be contaminated by nearby shale gas activity. And if it happens, it's very rare. Okay, first I want to show you what a leaking well looks like. There's a video. This is the production casing. This is the steel pipe. It's the last one to go down. It goes all the way down to the end of the well. It's the one that gets perfed. It's the one through which the hydrocarbons are supposed to come to the surface, but only inside of it, not outside of it. So this is water that's accumulated in the cellar of the well. The area around the wellhead is excavated. Water accumulates from snow melt or rain, and that bubbling is proof that that well is leaking. That's methane or other gases leaking from outside the well. All right, so you got to visualize this. That well goes down 5,000 to 6,000 feet. It's in Dimock, Pennsylvania. It goes out 4,000 or 5,000 feet, and the well is leaking. So the methane that's coming up outside the well could be going through somebody's water table, and even if it isn't, it's being exhausted into the atmosphere as a very potent greenhouse gas. Okay. So the question, number of questions: how many wells are leaking? When do they start leaking? What are they leaking? What's the probability that a leaking well is going to contaminate a drinking water well? Those seems to be reasonable questions to ask. First, why do wells leak? Because it's really hard to build a well that doesn't. If you poke 100,000 holes in New York State into the Marcellus and the Utica, you got to gasket each hole. Every hole you drill is larger diameter than the steel pipe that goes down. I think that should be readily obvious. Got it? The hole that you drill has to be larger in diameter than the steel pipe you put down, which leaves a gap between the outside of the steel pipe and the inside of the hole that you drill. If you don't fill that gap, if you don't put a gasket in there, anything that's in the rock formation can come up outside the well. What do you use for a gasket? Hardened cement paste. Not concrete, not reinforced concrete, not rubber, not some exotic polymer. You use hardened cement paste. Cement powder, water, and some chemicals. It's been used since the beginning of time in well drilling. Is it better now than it was 20 years ago? Yes. Is it a hell of a lot better than it was 20 years ago? No. There's only so much you can do with cement and water. You can put an additive in it that makes it shrink less. As you know, when cement cures, it shrinks. You can put an additive in it that makes it less likely to crack. You can put an additive in it that decreases its permeability, and that's typically, additives are typically added, but that doesn't mean that your cement is never going to fail. Here are just a couple of ways in which cement failed. We could talk for hours about cement failure mechanisms. The literature of the oil and gas industry is full of papers and reports on why cement fails and what causes each mechanism. For example, here's they did some laboratory tests. They pulled some casing. Here's the surface casing. Here's the production casing. This would be like 4 inches in diameter. This would be like 6 inches in diameter. This is the cement. Notice that there are shrinkage gaps. If they don't clean out this area called the annulus before they insert the cement is not likely to bond very well to the steel casing. That's just one of a number of possible failure mechanisms. How often do wells leak? I'm going to show you 3 sets of data. Industry data. I'm going to show you the source of each source of data. This is a 2003 paper. This is data from offshore oil and gas wells. No shale gas wells here. This is just offshore oil and gas wells. Doesn't matter whether it's a shale gas well, a water well, a gas well, an oil well, offshore, onshore, they're all drilled the same way. You drill them, you oversize the hole, you insert the casing, and you cement. So here's data on 43,000 wells. This is the age of the well, and this is the percentage of wells that are leaking by age. SCP is sustained casing pressure. There should never be any gas pressure in an annulus. If there's gas pressure in an annulus, that means that the cement has failed. Brand new wells leak at the rate of 5%, 1 in 20 leak initially. As wells age, the leak rate goes up. Partly because as the wells are aging, you're looking at wells that were drilled longer before. They're aging, but the technology probably wasn't as good. This is not definitive data. This is not prognosticatable. You can't use this data to tell me how many wells are going to fail in New York State if we start doing shale gas development in New York State. You wouldn't believe that. I wouldn't believe it. It's interesting data. Fast forward 2009, onshore wells. 360,000 of them surveyed in Canada. No time to go into the details. Something like 2% of the wells were failing immediately, and as they age, the percentage of failure goes up. Different numbers, more modern wells. One of the aspects of this paper, which is very extensive, it's used throughout the industry, it's called the kernel paper, the cardinal paper. If you want to find information from the industry about well failures, this is the paper everybody cites. As part of this paper, they went into an area of Alberta and studied a few tens of thousands of wells. Wells that were vertical and wells that were deviated. And they found something very interesting. This is all wells put together. When they looked at the difference between the wells that were vertical, that's yellow, and the wells that were deviated, that's pink, they noticed something. Deviated wells fail at a much higher rate than vertical wells. That's well known in the literature. I can point you to any number of papers in the industry literature that points out why one would expect well failures to occur more frequently in deviated wells. By definition, all modern shale gas wells are deviated. I would not use that data to predict what will happen in New York State because very few of those wells were shale gas wells. Here's the data I would use. I would go to Pennsylvania, because I just told you that over the last 5 years, there have been 6,700 plus shale gas wells drilled in Pennsylvania. Let's find out how many are leaking. You can do that tonight. You got nothing better to do tonight? Go home. And I'll point you to the website. It's the Pennsylvania Department of Environmental Protection Violations Database. It's a big spreadsheet. It has data on every single Marcellus well that's been drilled in the state. And it summarizes all the violations that have been issued for all kinds of things that the operators did wrong, including allowing their wells to leak. It's a violation. It's against state law in Pennsylvania to allow your well to leak. Companies don't want their wells to leak, but they do. The question is, at what rate? So this is data that I would use to predict the rate at which wells would fail in New York. Why? Because it's in the Marcellus, it's recent data, and it's the same operators that will be operating in New York State using exactly the same technology. So 6% failure rate in 2010, 7% failure rate in 2011, 9% failure rate in 2012. They're not getting any better at this. And there are reasons in the literature for why things would be expected to get worse. When economic conditions get bad and you're not making much money, you start cutting corners. Who said that? Watson and Botchett, industry people. You can read this paper. It's a wellspring. When the price of gas or oil goes up, there's a boom. There's a lot of wells that are drilled very quickly. Corners are cut. When the boom goes down and you start losing money, your best people are pulled off the job. Small operators come in where large operators left because large operators have too large an overhead to make any money. Small operators have lower overhead. They can make money by cutting corners. They don't have the best technology. They don't have the best people. Well failure rate figures go up. This is predictable from previous industry data. So if you're going to have between 50 and 100,000 Marcellus and Utica wells in New York, how many are going to fail? You do the math. Any one well failure can, I didn't say will, can contaminate any number of water wells. A failed well does not necessarily contaminate a water well. Depends upon the hydrology. Do we know the science of how frequently a failed well will contaminate a water well? No. Why not? No one studied it yet. Next thing, if an inspector goes to a wellhead, remember the video I showed you? So an inspector goes to the wellhead with a camera, looks down into the cellar of the well, sees that it's bubbling. Is that proof that the well was leaking? Absolutely. Let's do the inverse. Inspector goes to a well, looks down with a camera or a sniffer, doesn't see any bubbling, doesn't detect any leaking. Does that mean the well isn't leaking? No. If a well is leaking, does it have to show leakage right at the wellhead? No. Proof. Another video. One proof, there are many. See that bubbling? That's methane. There's a layer of shale. The nearest well is 2,700 feet away. Inspectors went to the well, didn't see any leakage. Well was leaking. They did isotopic analysis of that gas, determined that it's the same gas that was being produced by that well. The well was leaking and the gas is migrating underground and it comes to the surface wherever it wants to, wherever nature says it can. So these data are underestimates. More wells are leaking that have been found to leak because the only place they look for leaking is at the wellhead. How would you go about determining whether there was leakage other than at the wellhead? How do you do that? It's a good question. It's a science question. I want to find out in a region, say Tioga County, how many wells are leaking by not only looking at the wellheads, but by looking over the entire region and detecting how much methane is leaking into the atmosphere. You do what we did at Cornell. You get together with a professor at Purdue who has his own private plane, and professors at Penn State who are very interested in this problem, and they put a methane detector apparatus in the plane, and you fly around the county for days and days and days, and you take readings of methane concentration.